Okay, here we go. All right, so Kinley Parker, I hope you appreciate this, is all I got to say.
Love you, Kinley.
And I hope it works out. All right, so far is we have our DNA strand. What is this part called?
Replication bubble.
I really did want y'all to tell me. Okay, so that's the replication bubble, okay? What is this part called? The fork. Okay, so replication fork. All right, so you've got your two DNA strands, and they're held together by what kind of bonds? Hydrogen. All right. So the first thing that happens, we've got to create a replication bubble because, and you don't, I think we may have already drawn this. I don't remember if we did or not, but to give you an example of what I'm talking about. All right. I want you to look at this, okay? All right. If these were our two strands of our DNA, and we had A, T, C, G over here, what would we have on the other side?
T, A, G, C.
All right. Okay, now, what we're doing with this replication bubble is we're going to come in and bring in nucleotides, and there's going to be nucleotides that attach to one side, nucleotides that attach to the other side. So what would attach to the A? T. What about the T? A. G, C. All right, and then what about to this side? A.
T, C, G.
Okay, now look at both strands.
They're identical.
They're identical. Okay, so the way that they said with the semi-conservative model or the method that you're going to have this replication bubble and the new nucleotides are going to be brought in and it's going to make two identical strands by doing that. Okay, so that's what we're shooting for when we're going through this big process, okay? All right, so on this end, we said that this was our 5' end. Okay, so this is our 3' end. Okay, I didn't mean to do that. Okay, there we go. All right, so the opposite of that on the other strand is going to be what? Underneath the 5' is going to be 3' to 5'. Okay, because they run anti-parallel. All right, so when the helicase goes through, the helicase breaks the hydrogen bonds. You can remember that, H for helicase, H for hydrogen bonds. So it's breaking through the hydrogen bonds. It's becoming separated. You get this replication bubble. There are going to be lots of replication bubbles all the way through the DNA strand because it just speeds it up. Remember, the whole purpose of an enzyme is just to speed up the reaction. So that's why it's doing that. All right, so you have an enzyme that comes in, and it is going to create a point of origin, the origin of replication. What is going to get us started with that? The primase. All right, so RNA primase is going to come in, and it's going to create a starting point for this replication to take place. All right, so just like primer on a wall, you're going to have RNA primase that comes in and lays primer down. So it says, hey, this is our first couple of nucleotides. This is where we're going to get started. All right, so then after that, you've got an enzyme that comes in, and on the 3' end, whoops, it's going to lay down a new nucleotide. All right, so that's going to be right here. It'll attach right here, right here, right here. What's doing that? All right, DNA polymerase, and it's going to be polymerase 3 because there are multiple polymerases, and this one just happens to do this job, okay? All right, so here's our big DNA polymerase enzyme, and it's coming in, and it's laying down our nucleotides, okay? All right, we can remember what it does because it has the word polymer in it. All right, it's ACE, so we know it's an enzyme. Polymer is telling us that it is coming in and laying polymers, or it's created DNA polymer from the monomers, which are what? Nucleotides. So it's just putting nucleotides on top of each other to create a DNA polymer. All right, now it is going to work in this direction, the direction that we just went. Okay, it's going this way. And people get confused on this part, okay? Because what is the rule about the way that DNA strands are made? They have to be made how in regards to what prime? 5' to 3'. So that's telling us that this end is 5' and this end is 3'. Well, they get confused because they look up here at the template strand and it says it's 3' and to go into 5 prime, and they're saying, well, it's going 3 prime to 5 prime. No, no, no. You're not going by the template. You're saying that the new strand that's being built is going 5 prime to 3 prime. And remember, it's going to be opposite. When we had the people standing up and we were 5 prime, 3 prime, okay? And remember, across from them, it was 3 prime, 5 prime, because they're anti-parallel. Got me? Okay. All right. I don't know if y'all are just being quiet or if y'all are like, oh my gosh. Okay. All right. So, this strand, because it is going in order and it is following right behind this helicase, okay? So you got your helicase here that is leading the way, and you have this DNA polymerase that's just following right behind it. It is being led by the helicase. Helicase is breaking the stuff and it's following in right behind it, just making a new DNA strand. It can do this at about a rate of 50 nucleotides per second in human cells, 500 per second in bacteria. So pretty stinking fast. All right. So it's being led by the helicase. So for that reason, we call this, and I'm going to run out of room, so I'm going to write this up here, okay? But it's our new strand that we're making. It's called our leading strand, okay? Leading strand is being led by the helicase. All right, so that's how you can remember which one is which. Leading strand is being led by the helicase. It's going in the same direction the helicase is going, following in just right behind it, okay? Now, there's going to be a problem on this next strand because notice the template is 3 prime to 5 prime. So if we're building 5 prime to 3 prime, we're going this way, right? Because it's going to be the opposite direction. Okay, if we did that as one complete strand, we would have to wait for the entire DNA molecule to get unraveled before we could start on that end, on the left end in this case, and work our way all the way back down to the right end. Well, we don't have time for that. Okay, this is happening fast.
So I put down some more primer.
All right, so we're going to put down some more primer. But instead of doing it all in one long section like the leading strand, we're going to do this in fragments. Okay? So the RNA primase is going to come in and say when the helicase was right here and had just created a new, you opened those hydrogen bonds and made this part of the bubble, where the RNA primase comes in and it adds a little primer right there. Okay, so this is our primase again. Okay, all right. Well, we've got to work. We've got to work in making this this part of the bubble. So when our RNA primase comes in, we're going to put our DNA polymerase is going to come in right behind it because remember we've got to go this direction. Okay, and it's going to add nucleotides there. All right, you got me? Okay. All right, well, the RNA bubble opens up a little bit more. And right behind it, your primase is going to come in and start another little point. And then the DNA polymerase is going to come in right behind it and add nucleotides this way. All right? Okay, so that's your DNA polymerase right there. Okay, making a new strand. All right, did we get all that yesterday? We did, didn't we? Okay. All right. When we were looking at DNA replication, trying to figure out how it all took place, we got that the DNA, the leading strand, we understood, hey, that's easy. Helicase is unzipping the hydrogen bonds, and this DNA polymerase is just going right in behind it and just making this new DNA strand. But we couldn't figure out how the other strand was being made because we knew it could only go 5 prime to 3 prime, and it would have to wait for the whole thing to be done before it could start and build it the opposite way. So a Japanese scientist, last name Okazaki, okay, discovered how this takes place. That the primase, instead of laying down one time and going, it's laying down multiple times in these little fragments. And so he, wanting to take credit for his work, which is fair, okay, he discovered it and did the work, so he said he was going to name this little discovery after himself. So these little fragments right here that we just drew are called Okazaki fragments. okay? Your Okazaki fragments. Now, I'm having to write really big on this little screen, but that's these little fragments right here. So that fragment, those little pieces, those little chunks on that new strand, it's going to be, okay, hold on, I'm going to show you right here. Okay, so here to here, that's an Okazaki fragment. Here to here, Okazaki fragment. Okay, so from here to here, Okazaki fragment. Here to here, Okazaki fragment. Okay. Okay, so there's our little Okazaki fragments we're making. Okay.
Are these on our
Notes, it is. It is. Okay. So now when these Okazaki fragments are being made, they eventually will run into the next Okazaki fragment beside it. Okay? And so then that's how you get your one continuous strand.
And then that thing that just drops off and goes make more.
Yeah, they'll just keep making. It's gonna follow in behind that helicase and put another little fragment and then keep building 5' to 3'. Okay? Alright, so the only thing is you have fragments. You don't want to leave them as fragments, even though they run into each other and then stop. They're still individual fragments. So, fortunately, we have another little enzyme that's going to come in here. Yeah. Come on. I don't know how to change the color on that. Okay, it's going to come in between the Okazaki fragments. All right.
Oh, so that's another enzyme?
Uh-huh. It's going to come in right here. All right, now, on yours, you may want to draw it down here at the bottom and draw an arrow up. That's fine with me. If you want to do that and put your arrow right there. All right, this enzyme, its whole job, it's called ligase. And ligase is glue. Okay? It is going to glue the Okazaki fragments together.
How do you spell that?
It is Ligase. Yeah, it's right over that little watermark, or behind the watermark. All right. Ligase. Well, it's just a little bubbly enzyme. No. So, here, let me show you what. Let's see if I can erase. Okay. So, if you want to, instead of drawing it over your stuff, if you want to make your DNA strand, and you can just take that, draw it down at the bottom, like I said, and just draw an arrow up, then it's going to create glue. It's going to glue those two fragments together. Okay? To make them one. Exactly. Right. The enzyme is ligase. It's ligase. Gase. Okay? Alright, so that's ligase. Alright, now this is going to keep, okay guys, listen. This is going to keep happening in all of these little replication bubbles until eventually they all run into each other and you have one big DNA strand, two new strands. Okay? So that's replication. We're making a copy. All right.